Okay, you'll see in the future here where we discuss why light can be considered a particle. Um, but I'm going to show you why light can be considered a wave, and the reason is because of interference. And of the other phenomena that we've seen, some of them can be explained away according to it being light, being a particle. But this one definitely kind of shows that it's a wave. And so let me just illustrate what the double slit experiment is first. Double slit experiment is simply this. If you have, like it describes, two little slits. Okay, these are two little slits. And here comes, I'm going to call it monochromatic light source. What that means is basically one color. You can consider it like a one color light source. And as this light comes through here, what you'd expect is, here's a screen. Okay. So imagine if light came here, and here comes like a wave coming here like this, a wave front, and as it comes through, what you'd expect is that light should go through here, and eventually hit the other side, and what you get is a bright spot here and a bright spot here, and everywhere else would be dark. This would be if it were a particle. Unfortunately, it doesn't behave like this. This is not what happens. Okay, this is actually not what happens. What we observe to happen is this. Okay, so if you have the same idea again, double slit, here's a screen, what actually will happen is you will get a series of light, dark, light, dark, light, dark, light, dark, light, dark spots. Okay, kind of an unusual thing, not just two. And so what's actually happening here is there's an interference pattern. You can reproduce this very easily in like a wave table. If you have a wave table in your science lab, you can actually show how waves will illustrate this pattern. And actually we'll do this if you have like 2 point sources, let's say, going up and down in the water. But the young double slit experiment also demonstrates this wave-like pattern here. And so let me just explain this here. So what you can have happening here is I'm just going to make, here's the central line. Okay, here's the screen. What will happen is you'll have, let's say, a wave coming here, going along and hitting the central, a wave coming along here and hitting the central. Well, if these are coherent wave sources, they'll be in phase. In other words, these are waves in phase. Just to remind you, there's one wave, here's another wave that's in phase. They both match up exactly. They would both have constructive interference because they both match up exactly. Well, here you can see that it moved the exact same distance as this wave. And so they move the same distance going towards the center. And in fact, the center, you should have, I'll just put a plus here for constructive interference. Just off to it, you might have destructive, okay? But right here, you'll have constructive. The reason you'll get destructive in some spots is because, let's say a wave comes up here, and another wave comes from here. Well, what happens is they can be out of phase. And what happens is maybe the trough of one meets up with the crest of the other, in which case you'll get a dark spot. Right here, I'm just going to call a negative sign to indicate a dark spot. Okay, so you'll get some places where it'll be constructive and some places where it'll be destructive, depending on how far they've moved. Well, let's mathematically look at that description of how far they've moved. I'm going to just recreate that scene here, and if you have the double slit, the same thing again. And I'm going to just say, you know what, here's two wave sources. Let's say one going up here and another one coming up here. And let's say at this point here, there is constructive interference. Okay, at this point. At this point, there's constructive interference. Let's take look mathematically at what's going on. I'm going to just use a different color here and say, here's my central line. We know here, okay, that if there's constructive interference, this path here of this wave is actually slightly longer than this one. Again, we're exaggerating the picture, but this one's slightly longer than this one, which means that I'm going to call this right here, okay, this little triangle here, that's a right angle there. This right angle triangle here, this distance right here would be, this would be the extra distance. Okay, it's the extra distance. Well, if these are both coherent sources and they're both lined up, as long as this extra distance was some multiple of a lambda, it'll work. If it's lambda, it'll work. If it's 2 lambda, it'll work. If it's 3 lambda, it'll work. Because every single time, they'll both meet up exactly crest to crest or trough to trough, and you'll get that constructive interference. So we want that to be the situation. Well, it turns out some angles here we can look at, and I'll let your teacher run through this here, but essentially, there's an angle here. How do I show this? If I look at right here, there's an angle that goes up like this. Okay, so this little angle right there. Turns out that's the same thing as this angle, theta. Now, if you look at this, we're going to call that d, the distance between the slits. Okay, we'll call it d. Here's lambda, which is why in my equation sheet, what you end up getting here is you end up getting an equation that says that d sine of theta. Now, d sine of theta, well, sine of theta of this angle will equal lambda over d. Okay, so I'll just show you that here. Sine of theta will equal lambda over d, which means d sine theta will equal lambda. But in this case, I'm going to write here m lambda, and the m just means as long as it's a multiple of the wavelength, okay, this will occur. In other words, if it's 1 times lambda, 2 times lambda, and 0, if you put 0, you get this. Okay, you get this, what's called the central maximum. Okay, this is called the central maximum. We call the places where there's constructive the maxima, and where there's destructive we call them the minima. Okay, plural for minimum. So maximum, the central maximum, and the first one on either side, where m is equal to 1 on either side, we call that a first order maxima. Okay, this m equal 2, second order, m equals 3, third order, etc. And they just go on either side. Again, you're going to get light, dark spots. So you get this equation for constructive. That's for constructive. Destructive then would look almost identical. It would be d sine theta equal to, well, we don't want it to be differing by a lambda. We want it to be a half a wavelength, so they're out of phase. In which case, I'm going to write here m plus a half lambda. And the reason I can't just write half lambda is because I can't have whole multiples of that. So this way, if I have 0, the first one would be half lambda. That would be their first dark spot right there. Looking at a graph of all these, if I was going to chart the intensity, okay, so here's an intensity graph. The light would be the brightest here in the center, and it would look the biggest. And then it would die out as I move up. Actually, I should go this way. It's going to die out as I move up. And then it gets brighter and brighter and brighter, but not as bright as the first one. And then it dies again, and as I keep going, it'll look something like this. Okay, so in other words, you'll have the central maximum, the first order, second order, third order, and the same thing on the other side. It'll be symmetric, going down the other way, and it'll just kind of taper off like this. This would be what your graph looks like for a double slit experiment. Just to kind of save time here, I'm going to look at a single slit, and the only difference between a single slit and a double slit is that, just so you're aware here for graphing, is that a single slit looks something like this. I'm just going to show you the chart of it. Okay, so for the single slit, where D represents the width of the slit, you're going to get here that the chart would look something like this. It'll be a big intensity in the middle, and then little ones on the end that are kind of dying out. It's a little different. Okay, so in other words, whereas the one previously was this is for double slit, they're all equal width. Okay, this one actually ends up being twice as long. So in other words, if this distance here, I'm just going to call it as A, this would be 2A. Okay, so it's twice as wide. It's very wide to central. And then each one is actually the same height, whereas the other one, they kind of taper off. So just notice the difference between these two. Okay, there's for single slit. On often, okay, there's for single slit. Often in these single slit and double slit experiments, instead of using the double slit, what's often used is a diffraction grating. And a diffraction grating is just basically, think of it as like many slits. The only difference is that the lines will be a little bit crisper than this. They'll be a little bit sharper, okay, and a little bit brighter. So they're kind of nicer to use a diffraction grating. I'm not going to get into the mathematics, but it's nicer to use because of that fact. It just ends up giving you a sharper, clearer image than a double slit. And the first experiment was done with a double slit, and then it was found later, it might be more beneficial to use one of these. Just one final thing about the double slit experiment that I want to go over is with regard to the some mathematics behind it. And if you look at the math involved in here, okay, the other equation that you can get that I have written there is that xm is equal to m lambda L over d. This simply is saying, now this is your length L. There's L. lambda is, of course, the wavelength. M is some order, and D is the width of the slit. Xm just refers to that. If I'm looking at x1, it would be how far this distance is. That would be x1, how far this distance is. It would be equal to this distance. x2, okay, would be how far it is from the central to the next one. So they're always with reference to this second one. It's a nice little formula. Let your teacher work that out, but it's a nice little formula to help you look at how far these are from the central maximum.